good afternoon, everyone. My name's Kate, and I'm a Business Development Manager in the CPD unit at Cardiff University. I'm really delighted to welcome so many of you to this session this afternoon, and thank you so much for joining us today. Just to reiterate that we're going to be taking some questions towards the end of the session, but feel free to use the Q&A facility, and I think there's going to be some sort of interactivity throughout as well. So now I'd like to introduce you to Dr Matthias Treder, who's going to take today's session. Thanks very much, Matthias.
Can you hear me well? Yes. To start with a little bit of housekeeping, so the talk will be a little bit interactive. So there's, I think, 2 slides where I'd like to ask you, I'll ask you a question, and I'd like to post the answer in the chat box. And just to be clear, we're not being judgmental. So this is just so we need a broad as possible participation. And the point will just be to bring over some points I want to make. So what I'm doing now is to try to share my screen. So let's jump. Can you see my screen well? Yes, okay. So we jump straight into the presentation. So I'll start a little bit with introducing myself. So I'm a lecturer in computer science at Cardiff University. My interests are in machine learning and specifically in machine learning applied to medical imaging. So that's my background, and that's kind of the kind of reasoning and some of the examples I'll show stem from my background. So to jump straight into it, maybe I'll start with telling you what this talk's supposed to be about and what it's not supposed to be about. So this presentation is really about introducing some basic concepts in machine learning and the terminology on a conceptual level, and briefly discussing some application areas in industry and business that might be interesting or relevant to you. And I'll jump into 2 specific topics which gain a lot of attention in machine learning, which is natural language processing and image processing. And then we have a short technical dive into machine learning, just to explain some of the concepts. That will be a small part and not that important to get the whole message. And just to be clear, so what this talk is not about is, I'm not really showing you a practitioner's perspective. So I'm an academic. I'm mostly doing academic research on machine learning. I'm not really working in a company and applying machine learning on a daily basis. So I'm also not going to be listing commercial tools for machine learning, such as AWS or Watson. And I'm also not. There's a lot of other aspects to machine learning that are important. One is ethics and biases. There was a wonderful talk on that on Monday. I won't have time to go into that either. All right. So to get started, let's maybe get one term out of the way and make sure we all understand what data is to start with, because we'll be talking about data a lot. So essentially, everything we can think of, a book, for example, which is a collection of letters. Data can be a video, which, on a technical level, we can see it as a collection of color values. So this is a black-white video, so it'll be a collection of gray values. Of course, we have things like USB stick, which contains data. We can have music, which comes in waveforms. What all of these have in common is that we can represent them by numbers. So we can somewhat transform them into a numerical form. And that's, of course, important, because the only thing computers are able to work with is numbers. So there's always, implicitly, there's always kind of this transformation step. Kind of to define data in a one-liner, we could say data is a set of values of qualitative and quantitative variables. So what is a qualitative variable? So that's a variable that takes on a small number of different values. For example, sex, so it could be male or female or non-binary, could have ethnicity, or you can have the country of birth. Quantitative variable is something so it's more on a continuous scale. So this could be weight, height, or income. An essential point from the perspective of data science is that data really requires interpretation. Once we can interpret the data, it becomes information, and that's what we want at the end. We want to, we want to leverage data to gain information and to increase our understanding of a particular problem. All right. So let's delve into why machine learning is useful and in what areas it is useful. And to start off, I'd like to stress, or let's have a look at the vast amount of data that is being generated. This is an information sheet from Raconteur, and I'm not going to go through it in detail. I'm just going to highlight a few parts. So this is essentially the amount of data generated per day. There's roughly 500 million tweets being sent per day. There is 294 billion emails being sent every day, and so on. Just looking at these stats, and this is ever increasing. So these numbers are increasing every year. Just looking at this, it's clear that there's no way that humans are able to leverage this data or even process this data. So if we need to process this data, or we want to gain understanding of this data, we need some kind of algorithms or some kind of automated tools that do the job for us. Now, what are some of these tools? So on this slide, I'd like to highlight some machine learning applications that you've kind of encountered in your daily life, and you've probably encountered most of them in your own lives. One is if you're doing online shopping, say on Amazon or any other company website, there's a machine learning tool used called recommender systems that is used. Essentially, you buy a product, and then let's say the website tells you, oh, you may be interested in this product as well, or the other product as well. So what the company tries to do is, based on your purchase history, they try to predict what other products you might be interested in. And for this, they use your own data, so the purchases you made in the past, and also data of other customers that maybe had done similar purchases as you and then went on to buy other products. If you're not so much of an online buying person, then you're maybe an offline buying person. And you've surely encountered self-checkouts in Tesco or Sainsbury's, for example. And they use machine learning to recognize to read off the barcodes from the products you're holding into the scanner. So it's a somewhat simpler problem, but the barcode can be a bit skewed or squeezed, so it's not a trivial problem to solve. Another one is you surely have an email program. So there's always a spam filter operating in the background, and the spam filter is a classifier, tries to decide whether an incoming email is legitimate and you should read it, or it's spam. So it does this decision based on looking through the text in the email and making an automated decision. A somewhat more sophisticated AI tool is this kind of personal assistants, such as Amazon's Alexa or Google Home, Apple Siri. These assistants you can talk to, you can interact with, you can give them tasks, they can talk back to you, and we'll delve into this topic a little bit more later on. If you ever use a camera or you make photographs, you see that sometimes you see this little red rectangle around faces. So this is a face detection algorithm. It detects where in the image a face is. A very sophisticated example of machine learning in the wild is self-driving cars. They have to solve the task of monitoring the environment using cameras or LiDAR. Not only monitoring it, but also understanding it. Which part of the environment is an obstacle, which part is the street, which part is other cars, and then taking decisions in an automatic way. Then we have face recognition. So it's the further steps. Once you detected a face, try to recognize the face. And it's something Facebook is doing. Sometimes it's, if you put on a photograph on Facebook, it might tag you automatically. So essentially it's detecting that there's a face and detecting that it's your face and then tagging you automatically. It's also something that's happening on airports. If you go through an automated check, you have to look in the camera. So it scans your face and it also, it also detects it and matches it with the database. The last example on this slide is text completion, where let's say if you use, for example, Gmail, and you would type the black part of this text, so thanks, I will have, based on what the email you're answering to is about, it might propose to complete the text. For example, I might have a look and get back to you. So this is yet another example. And here we come to the first interactive part. So if we look at all these kind of daily examples, and let's leave out recommender systems for now. There's two themes here. So there's two kind of big topics. And I wonder if you can kind of figure out what they are. And can you maybe just write your associations in the chat box? And maybe Claire can tell me in a minute what kind of associations go in there. So just look at the kind of big picture that combines these things, and leave the recommender systems out for now. So I'll give you maybe half a minute for that. So anything coming in yet?
So we've got some answers coming in saying image processing, NLP, security, visual relevance, language, images.
Okay, wonderful. Very, very good, very sophisticated answers. And actually, the ones I had in mind, we've heard them twice. So one thing that was mentioned is language. So all of these on the left side, whether it's spam filtering, Alexa, or text completion, it has something to do with human language and processing language. And I think image processing and images was mentioned here. So indeed, this is about using a camera to record images or videos and somehow make sense of them. And this field is called image processing. And we'll delve into both of them a little bit later on. All right. I'll just quickly run through some other applications. So this is kind of some of the things we encounter in daily life. There's many more that maybe you are not aware of, or we are not aware of, but they happen in industry. For example, in manufacturing, we have maintenance, prediction, condition monitoring. In travel and hospitality, if you go on websites, the pricing is often dynamic, so it's based on what kind of purchases have been made in the recent past. In energy, the companies try to use machine learning to predict the energy demand in particular times of the day or particular days of the week, and also optimize the supply. Healthcare and life sciences, we've got disease identification, which is automated. Machine learning is used in drug discovery. It's used for risk analytics and stock market value prediction, financial services. And as you mentioned on the previous slide, security is another topic that involves also computer security. So if your company is wired up to the internet, you might want to detect malicious activity or hacker attacks, stop the attacks. And again, machine learning is used for these purposes. And lastly, maybe some of you work for, represent a small or medium-sized business. So the question is, what kind of, how could you leverage machine learning in this kind of businesses? And there's just a couple of broad ideas. One being business analytics. We say we use machine learning to make sense of, let's say, all the financial data and the turnover and all the money flow and all the data we have to make future predictions. One could be optimizing customer interaction. So if you interact with the customers via a website, you can use a digital assistant or chatbots. They're getting better and better. Analyzing customer feedback. So there's algorithms. Let's say if you have a lot of customer feedback, maybe you want to measure how positive or negative it is based on the text. and this is an area called sentiment analysis. So there's tools out there for that. Improving HR and recruitment. If you represent a big company and you get like hundreds and hundreds of let's say applicants, there's automated tools to work through the, let's say, the CVs and maybe highlight some of the applicants that stand out. And lastly, there's the security aspect, which of course often also applies to small and medium-sized businesses. All right, so I'd like to change gears now. So now we've seen a few applications of machine learning, in the world around us. We haven't really talked about what it actually is. So I'll try to delve into that a little bit in the next slides. And there's a couple of definitions, maybe, so I found this one, which I can read out for you. So it says machine learning is an application of artificial intelligence that provides systems the ability to automatically learn and improve from experience without being explicitly programmed. And here I've underlined the word learn. So as a contrast to kind of standard computer programs where you would tell the computer exactly what to do in every step, in machine learning, you program, the computer program itself is a learning algorithm. So you write a program that is able to learn, for example, from seeing examples to make predictions in the future, learning from experience. And we'll see a bit more what that means on the next slides. So typically speaking, people subdivide machine learning, let's say on the academic level, it's subdivided into 3 areas. And I'll just go through them very briefly, just to drop the terms. So one area is called unsupervised learning. Here we have a bunch of data. We don't really know what it means. And that could be, for example, let's say your Facebook, you have all the users on Facebook. You have the, some of the interactions, which users are talking to which users. You would like to identify maybe groups of people who interact with each other a lot, but you don't really have data to build on. You just have this big bunch of data. You somehow want to make sense of it. So this is the realm of unsupervised learning. Then there's another big and very sophisticated area, which is called reinforcement learning. And this is something that people often associate with, for example, intelligent robots, let's say. So the whole idea of reinforcement learning is that you have an agent. So this could be a robot. It could be let's say, a character in a computer game that's somehow interacting with the environment. And it's interacting via actions. And action could be, walk forward, lift up a particular object. Whenever the agent performs an action, well, the environment changes and the state of the agent changes. So the agent is maybe in a different location, in a room, or has picked up a particular object, and it might get a reward. So maybe you want the agent to do something specific. If it reaches that goal, it gets a reward. And the whole area is inspired by the way humans learn as well. So it's learning by trial and error. And that's what the reward stands for. It's like positive reward or a negative reward. It's a bit like, when you imagine a baby trying to learn to walk, the baby stands up, falls over, stands up again, falls over. At some point it stands up, it doesn't fall over immediately. So somehow it adjusts the way it stands up. And this process continues. It's a trial and error process that continues on and on. Until the baby learns to walk. And essentially, reinforcement learning researchers try to do the same in machines, learning from past failures and changing the behavior such that the likelihood of success is increased in the future, roughly speaking. So the last areas that we're gonna mentioning here, and we're gonna delve into a bit more, is supervised learning. This is about classification and regression. Classification means you take some incoming data. I think a good example is the spam filter. The incoming data is an email. The spam filter has to decide spam or inbox. So this is a classical classification problem. It's 2 classes, spam or inbox, and the classifier has the text of the email as data to base its decision on. Okay. On this slide, I'll just give you kind of cartoonish presentation of what classification is really doing. And this is a little bit abstract. So let's imagine you have, let's say, patients in clinic, and you measure their blood pressure and the temperature. So this is here the x-axis and the y-axis, and each dot is one patient. Now you also know that some patients have a particular condition. Let's say that's the red ones. Some patients don't. That's the green ones. So what you would really like to do is, using the blood pressure and temperature measurements, you would like to predict whether somebody has a condition without doing the test. And the test itself could be very expensive. So maybe you can just use these two markers here, temperature and blood pressure, to make that prediction. And then what a classifier does, and this is just a cartoonish example of a linear classifier called linear discriminant analysis. That's not really important. What's important here, what a classifier really does is it kind of tries to separate these two classes. And this is represented by this dotted line here. So this is a decision boundary. This classifier would say everything above the decision boundary is a patient. Everything below is not a patient or doesn't have the condition. And then there's different classifiers which make different decisions. So for example, you see this classifier called support vector machine creates a decision boundary which is kind of more wiggly. So it also kind of fits this one correctly. But now what you're really interested in is in the future, you get in, let's say, a new patient, you haven't done the test yet, you only measure blood pressure and temperature, you want to predict whether that patient has the condition or not. And then you see that these two algorithms, which we have trained, so the first one on the top would predict that this patient doesn't have the condition. The second one would predict the patient has the condition. So this is the basic idea of supervised learning or classification. And kind of staying in the same analogy, just briefly go through the idea of unsupervised learning. Essentially, you have patients here and you don't know much about them. So you don't know whether they have this condition or not. But maybe you think that they form 2 or 3 distinct groups. And you can use algorithms called clustering for this. So for example, you might assume that there's actually 2 subgroups of your patient population. And clustering would use something like proximity to form these groups. And then, well, essentially, there's a choice you have to make here is to define how many clusters there are. So if you form 3 clusters, again, you have 3 different sets of patients that are formed by the algorithm. Okay. So this was our first dive into machine learning. We're going to go a step back now for a bit and talk about the 2 topics that you highlighted a few slides ago. So we talked about human language, so machine learning working with human language, and machine learning applied to image processing. And so let's start with the human language. Kind of to understand the complexity of dealing with human language, I think what we need to do is let's kind of decompose what actually happens when we talk to someone. So imagine you're the person on the left. You want to communicate some information to someone else. Let's say the information is, today during breakfast, your cat jumped on the table, hit your bowl with cornflakes with a paw, and spilled it across the whole table. So you want to get this thought, which is in your mind, this memory, into the head of the other person. So what's happening here on a technical level? Now, the first thing your brain is doing is converting this really complex thought you have in your mind into words, probably a couple of sentences they will need to explain this. And then the words are converted into an utterance. So it's somehow, the muscles in the mouth are used to produce the sound. And this is called encoding. So we have something complex going on in our mind. We somehow want to transform it into words and then spoken language. Now, once you speak a sentence, what it really is vibrations through the air, propagating through the air, arriving in the ear of whoever's listening to you, And now that person has two problems to solve. First problem is taking the sound and transforming it into words. Once you have the words, you still have to transform the words into meaning, because what you really want at the end is that this person understands what went on at your breakfast table this morning, right? And well, there's two things that could go wrong here. Sometimes you ask someone like, excuse me, can you speak up a bit? This means that the first step went wrong, right? So you heard the sound, but you couldn't quite translate it into words. Sometimes you might ask like, oh, can you explain this again? I don't get your point. Then really something went wrong in the second step. So you heard the words, you transformed them into words. You couldn't really make that step. You couldn't get from the words to the meaning in your head. Now I made this explicit because if you want to build a machine learning system that can perform all of these steps, you actually need to break it down that way. And for each of these steps, there's essentially a separate system. So one system is called text generation, auto captioning. So where essentially we, for example, in auto captioning, you present the algorithm an image, and the algorithm describes what's going on in the image. For example, a dog catching a frisbee. The next step would be text-to-speech synthesis, and this is something there's been research on that for decades at least. So basically, you have a bunch of text, you want to transform it into spoken, into a sound wave essentially. And then at the other end, you maybe get in the speech, you have to transform it into text. Once you have the text, well, you still need to understand it. And that's one of the hardest parts for machine learning systems, to really gain understanding. And they need to solve all of these 4 steps. So something like Siri or Amazon Alexa actually performs all of these 4 steps simultaneously all the time. And we can't really go into detail on the technical backgrounds. So I just want to mention one specific technical aspect. Because what I've said earlier on is that everything we work with needs to be transformed into numbers somehow, because that's how computers work. So computers are not very good at working with words. So a very important concept in this research field, which is called NLP, or natural language processing, is somehow transforming these words into numbers, or collection of numbers, which we call vectors. And as I said, I'm not really going into the details, but the way these numbers are created is you take a big text corpus, let's say Wikipedia, and there's algorithms such as Word2Vec, GLOV, and BERT. And what they do is they take all the words from this corpus and they place them, they give them some coordinates. So what we've seen here is X and Y coordinates. And what you want is transform the words into coordinates such that neighboring words should have similar meanings. And if you look at these examples, this is indeed the case. So for example, we looked at microwave. The word microwave is very close to the word oven in this space. Color is very close to paint, and hose is very close to sprinkler. So some of the algorithm managed to put the words in such a way that similar words are in similar parts of the space. And this is the important step that we make when we go from word into meaning, representing meaning or semantic relationships. And just one last detail point about this. So these spaces, they have really nice mathematical properties in that you can do arithmetics there. And this is maybe the most common example that people would give is, let's say you take the representation of the word king, a numerical representation of the word king, you subtract the representation of the word man, and you add the word woman, the word you get out is queen. So essentially what this means is that the algorithm has learned that the relationship between a king and man is the same as the relationship between queen and woman. All right. So this was our quick dive into natural language processing. let's briefly talk about image processing, and I'll give an example from which is medical imaging, which is kind of the field I work in. And let's say we have an X-ray image of a human. So the job of a radiographer is to look at X-ray images and come up with a diagnosis, right? So the question is, how does the radiographer know how to do that? Well, the radiographer looked at dozens, maybe hundreds of X-ray images during the training, maybe 1,000, probably no more. Looked at these images and learned to make a diagnosis, like this bone is fractured or this looks like a tumor. Now, what's the idea of machine learning here? The idea of machine learning is that an algorithm can actually look at millions of images and can do so in a short time. It can look at 10 million images within the span of an hour. So it has a much larger body, let's say, and it can remember all of the images if necessary and compare them all to the current new image. The idea, though, is not really to replace the radiographer, but kind of to form a conjunction. So maybe have an algorithm that, maybe highlights certain parts of an X-ray to the radiographer, or maybe solves the easy cases. If there's a broken bone, that's usually quite easy to detect. Maybe the algorithm can help you on that. Maybe the radiographer will have more time to talk to the patient, or to spend on the really tricky cases. So that's an example. And how do we know that? How do you actually know that algorithms are good at doing that? One reason we know that they are is there has been a image processing competition around for, I think, almost 15 years now, which is called IMAGENET. What is the task here? The task is there is 14 million annotated images, and you see 8 of them. The task is to predict which category the image belongs to out of 1,000 categories in this case. So for example, this one, second image is a container ship, third image is a scooter, fourth image is a leopard, and so on. And to gauge how good the machines are, we can compare it to human performance. So we can show the same images to humans and see how good they are doing it. And then what happens if you look at how the machines performed over time? So the first bar is from 2011. The last bar I have here is 2016. What this shows is the error that machines make at the prediction. So in how many % of the cases are they wrong? In 2011, 26% of the cases were wrong, whereas the human performance is around 5%. Now, there was a bit of a magical moment in 2015 because this was the first time an algorithm outperformed humans. So the human performance is 5%, and 2015 algorithm performed at 3.6% error, and it's gone further down since then. So we're now vastly better at solving tasks which are quite complex as this one. Machines are much better at that than we are at using our eyes. All right. So we've discussed some of the applications, and I've given you a kind of broad overview into the technical aspects. There's a little bit more of a technical dive here. I think there's one slide which is a bit technical, but it's not that important. So if that's too much for you, that's fine. It's not important to the message of this talk. Before we do that, I'd like to disentangle a few words that you might have come across. So people talk, about machine learning, artificial intelligence, and deep learning in kind of interchangeable fashion sometimes. Really, what most researchers agree on is that artificial intelligence is a wider field. So machine learning is part of artificial intelligence. But things like knowledge representation, symbolic AI, expert systems, these are other branches that also belong to artificial intelligence, but they're not machine learning. And then something you might have heard, a term called deep learning. That's again a subdiscipline within machine learning. And deep learning is really a neural network. And I'll have one slide, I think 2 slides about what a neural network is. We just quickly delve into that. The kind of rise in popularity of machine learning in the past say 6, 7, 8 years is mostly due to these neural networks. This is why it's worth if we spend a few minutes on that. And they mostly especially excel these two areas that we've talked about: image processing and natural language processing. So processing human language data. And one difference between what we call deep learning and all the other machine learning algorithms is a bit of a technical one, and I'll try to explain it on the next slide. And this is the notion of feature engineering versus feature learning. So what is a feature? A feature is some information or some data that we squeeze out of our input that is important to the task. If we think back to the example where we try to classify patients into having condition or not, maybe, and we measure blood pressure and temperature, let's say maybe temperature is actually not relevant to having the condition, but blood pressure is. In that case, blood pressure is the important feature. So both of these are features, but blood pressure is the important feature and temperature is an unimportant feature. So the algorithm somehow has to learn that. Now, classically in machine learning, what people did in problems such as, let's say, face recognition, classically what people did is they defined points in the face. There were 80 nodal points, such as the nose, distance between the eyes, and so on. They defined them, they measured them, they got the corresponding numbers according to these features, and we then fed them in an algorithm. And this is called feature engineering, because there's a human sitting there and trying to figure out what kind of features, what kind of measurements we could do could be useful for the algorithm. Now, the whole idea of deep learning is really, you kind of completely skip that step. What you do is you just feed the raw images, and a lot of photographs, you feed a lot of photographs to the algorithm, and you hope that it somehow learns what is important. And this is, without going into the details, this is a visualization of something these algorithms learn automatically without human interference. You know, they learn to extract particular parts of the face. They learn that, you know, an eye is an important marker of identity, because people's eyes may have different shapes. The nose is important, and so on. So this is something the algorithm learns automatically by exposing it to a lot of data. And that's the beauty and the richness of machine learning, is that we don't need to figure out what the best way is to solve the problem. The algorithm will figure it out itself. And this is the one more technical slide. What I try to explain here is give you a little bit of an intuition of what a neural network is, because I believe it's not actually that complex to understand. A neural network consists of little units which we call neurons, and this is represented here by this red disk. And these neurons, they perform very simple mathematical operations. So I'm just going to talk you through this operation very briefly. So what a neuron really does is it gets information from previous neurons from another layer. And this information is just numbers. Let's say we have the number 2 and the number 3. The neuron weights this information. Weighting means it just multiplies it with a number. For example, the number is 0.5. So if I multiply 2 by 0.5, I get a 1. If I multiply 3 by -1, I get -3. So this goes into the neuron. It gets added up. 1 minus 3 is -2. So I get -2. And then the last step is a so-called activation function. So you put it into a function, you get something out. And that's the output of the neuron. And the neuron just sends it to the next neurons. If you understand this slide, or if you understand this principle, you understand neural networks and you understand deep learning, because everything's just built up on this principle. So just to summarize, it's just weigh the incoming information, sum it up, and apply some function to it. And there's a couple of different functions: linear, sigmoid, rectified linear unit. I'm not going to bore you with the details here. Just one last thing I would like to mention is what training a neural network really means is finding these weights, finding these W's here. Why is that? Because the neuron has to decide which information it thinks is important and which information isn't. And can do so by changing the weights. So if the weight is very small, it means the neuron doesn't consider the incoming information from that location as important, right? So somehow finding these W values is actually what training a neural network is about. And visually speaking, the way these networks get trained, you can imagine, just think of a landscape, and you are, let's say, a person walking that landscape. The height of the landscape is the error your algorithm makes. So the error in predicting, let's say, the identity of a person. So how many cases does it get wrong? So this is a measure of the error, and you can try to find out how does the error change if I modify these weights. So if I increase, let's say, if I decrease W by a bit, maybe the error decreases. And this is essentially what's happening. So we start at a random location, randomly initialized weights, and then we perform something called gradient descent, which is really looking for the location in the space where our error gets as small as possible. And this slide is all there is, essentially speaking, at the bottom of neural networks. So a neural network really is just a collection of these things. So I've just discussed one of these balls, and if you connect a lot of these balls together, you get a neural network. And usually we envision information flowing from the left to the right. So you might have some input here, such as blood pressure, age, BMI, and it's just passed on through the network. And at the end, the network makes a prediction. For example, what's your probability of developing condition X? Again, all it needs to know is how to define these weights, how to select the incoming information from other neurons. All right. Just very briefly, one last a little bit technical slide is to give you a notion of how image processing really works. And this is an image of a brain slice, but the same principle applies to any type of image. It could be a natural image. The way it really works is that patches of these images are connected to neurons in the following layer, and what is performed is something you can call that's in technical terms is called convolution, where you essentially take this patch, you move it across the image, and you try to extract particular features. This could be, for example, edges or particular shapes from the image. And you just do this a couple of times. And in every stage, you kind of, let's say, shrink the image, and you try to extract more and more of these features, or feature maps, as we call them. So the information flow here is from the left to the right. And at the end of the process, you've got a prediction. For example, since this is a brain image, maybe the prediction is this patient has a tumor or this patient does not have a tumor. And the way this is happening is that we're slowly transforming spatial information, so information about the pixels and where information is, at what location information is, into semantic information. Because at the end, we're not interested in really where the tumor is. We're really interested in is there a tumor or is there not a tumor in this brain scan. All right, so this was the technical dive. We're going to do one thing which sounds technical, but it's actually not. So we're going to train a network right now with your help. We all got a very powerful neural network in our skull. So I'll need your help now. And this will be another interactive part to train a neural network. And hopefully this will help us to understand some principles. So we train a neural network to perform classification. And what we want to classify is whether an image of a fish is a salmon or a sea trout. So I'll show you two images of salmon and two images of sea trout, and you have to try to figure out what a salmon is and what a sea trout is. So these are two images of salmon, and these are two images of sea trout. And I'm not a fishing person, so I wouldn't be able to tell the difference. Maybe you are, or maybe not. In any case, try to have a look at these images. I give another maybe 20 seconds. Just try to look at them, try to remember them, and try to figure out what a salmon is about and what a sea trout is about. Because that's essentially the problem these algorithms have to solve. And now we try to solve it ourselves. All right. So what I'm going to do now is I'll move on. On the next slide, I'll show you an image. And I need your help. The image will be a salmon or a sea trout, but I won't tell you which one it is. And please write in the chat box, if you just write salmon or write sea trout, just the word, whichever you think it is. And then hopefully Claire can tell me which is like the majority of people voted for. Okay, ready? So let's move on. So what is this one? Salmon or sea trout? Please type it in the chat box, and maybe wait a few seconds.
Sea trout is the overwhelming choice for most people, Matthias. So.
Okay, wonderful, thank you. Okay, and that's correct. Let's move on. What about this one?
Salmon. Everyone's saying salmon.
Okay, wonderful. What about this one?
That's more tricky. We're a bit mixed. We're getting mixed results on this one.
Okay, wonderful. It's actually salmon, but yeah, it's hard. What about this one?
Again, we're getting mixed reviews. Mixed
okay. Okay. Thank you very much, Claire. Actually, what happened is exactly what I hoped would happen. So we don't have too many fish experts in the audience, which is great, because I wanted to make 2 points. So I hope that you will get the first 2 ones right, and I hoped the latter 2 ones will be half-half, which is roughly what happened. So this is actually a sea trout. But let's try to understand what's going on here and why you got some of them. Why it was so easy to get some of them right, and why the others were so difficult. So let's look back. This was our training set. This is what it's called, a training set. So this is what we showed your brain algorithm. Let's call it an algorithm. For the test set, which I just showed you, these 2 ones were really hard. Well, and why is that? Well, they're actually not in the training set, right? You haven't seen them before. When I showed you this one, actually, you overwhelmingly said sea trout, so you got it overwhelmingly right. And why is that? Well, maybe you remembered that there's actually a fishing rod in the image, and you've seen that image before. So actually, what you did, you didn't really figure out what the difference between a sea trout and a salmon really is. What you really did is you remembered the image, right? And this is called overfitting. So it's something that algorithms sometimes like to do. If you show them the same image again, they just might have remembered that they've seen it before. You know, they just might remember, oh, I've seen it before, and it was a sea trout. I don't know what the sea trout is, but I know that the image with the fishing rod is a sea trout image. So this is why it's important, if you want to gauge the performance of your algorithm, you have to expose it to new data it hasn't seen before. So let me lift the secret. What is the difference between a salmon and a sea trout? So a salmon can be distinguished from a large sea trout by a more streamlined shape, concave tail, slimmer tail wrist, upper jaw reaching no further than the rear of the eye, and so on. I'm not going to read the rest. And on the right side, there's actually a list of features. And 1 column is for the salmon, 1 is for the sea trout. So for example, general appearance of the salmon, slender and streamlined, sea trout more round and thick set. So you would think maybe if you looked at dozens of salmon and sea trout images, maybe you would have been able to come up with that. You certainly would have had to see more of them. And this list of elements, this is something we want the algorithm to learn. So we don't want the algorithm to remember what it has seen. We really wanted to figure out what actually are the features that differentiate a salmon and a sea trout. And surprisingly, in many cases, actually the algorithm is able to figure this out implicitly. And this is the information of figuring this out is contained in the weights of this network. Okay, so I hope this was illustrative in this regard. And I think coming to the end of the talk. So just to wrap up what this was about. So I hope I made clear that machine learning is a useful tool for leveraging large amounts of data, doing so also in a very fast way. And we've discussed a range of industrial and customer applications. We delved a bit into two applications, natural language processing and image processing. We also discussed that there's three really different subdisciplines within machine learning: unsupervised, supervised, and reinforcement learning. And finally, that supervised learning is partly about a classifier, which has to learn. That's what we have done, right? We've learned from examples and corresponding labels. And based on these examples, we've learned to make predictions about future images, which is really the whole what the whole process is about. Okay, one more slide. So if you weren't familiar with machine learning yet, and I hope you found this talk useful, if you think about what are the next steps for yourselves, so there's a little bit of an advertisement on the left side. So at Cardiff University, in the School of Computer Science, we have the Data Science Academy, which offers MSc programs in data science, artificial intelligence. If you work for a company or you represent a company and you want to get engaged with the university, we have an interface for that. We call it the Data Innovation Accelerator from a website. It's targeting SMEs. They work collaboratively with companies to apply data science techniques to produce tangible benefits for the business. So if you represent the company, that will be the first point of touch if you think you have a problem that might be addressed by machine learning. Other than that, always feel free to email me with any questions about this talk or machine learning in general. If you want to study on for yourself, there's a host of other resources I can recommend. So if you're interested in programming, I would recommend learning Python or R, and probably Python is the better choice. The deep learning software frameworks, they're all the big ones are implemented in Python. There's two major ones right now. One is called TensorFlow, which is developed by Google. The other one is called PyTorch, which is developed by Facebook, and they both run in Python. There's a lot of great online courses. For example, on Coursera, there's courses on machine learning and deep learning if you want to self-study. There's some blogs. So this is a very personal selection. That's blogs and podcasts I like. I would just suggest Google. There's tons of others. I like to read medium.com, which has a lot of little blog posts about data science and machine learning topics. There's another blog called Towards Data Science, which is specifically about data science. Podcasts, there's a nice one called lineardigressions.com. It's a couple there in every podcast, which takes about 20 minutes. They're just picking up one topic in machine learning, and they're trying to digest it in a kind of conceptual way, which is really nice. And then there's the podcast by Lex Friedman. He's an AI researcher at MIT, and he's interviewing, he makes really long interviews, sometimes 1 to 3 hours of really, really big shots in AI. So if you're interested in the more, say, academic side of machine learning, I would definitely check this one out. And so with this, I'm at the end. I would like to thank you all for coming. I hope you found this useful. If there's any questions, now is the time to just put them in the chat box.
Thanks very much, Matthias. That was really very interesting. We have had a couple of questions in actually already. So Richard Lation is asking about finding lowest error by adjusting weights. So does a neural network need labeled data to decide that?
Yes. Yeah, and sorry, I didn't really, let me go back to that point. And I didn't really go into that in enough detail, but you're entirely right. Where is it? It's on this slide. Let me just get there. Yes, so this is the adjustment of the weights. So if we think of the salmon and sea trout example, essentially what you would do is, you know, feed it the 4 images, and they have the labels, and then you let the network predict, like, what is the probability that this image is a salmon, and the probability is a value between 0 and 1, and 0 means very improbable, 1 means I'm 100% sure this is a salmon. So you want the neural network to say that if it's a salmon image, the probability of the network should be 1 or close to 1. If it's a sea trout image, the probability should be close to 0 because it's not salmon, right? So then you can match, or you can compare the prediction of the network to the true label, to the true probability that you know, and then you can see if there's a disparity. And if there's a large disparity, you can say, oh, maybe, you know, let me tweak the weights in such a way that next time the neural network sees the same image, it makes a better prediction. And this is just an iterative process where essentially you can feed in the images one by one, and the network will just adjust its weights until hopefully it arrives at a good set of weights.
Thank you very much. There was also a question about the BERT model. Are we implementing that? Is that something that you can do?
To be entirely honest, I'm not working in NLP. I have it's mentioned here. So there is implementations of these models already there, right? So you can download them. If the question is about the technical details of BERT, I'm not that familiar with them, to be entirely honest. So I'm usually working in medical data and supervised learning applications. So I'm sorry, I can't really give you any technical details on BERT.
Thank you.
There is though. Sorry to interrupt. If you have specific questions, I have colleagues who are experts in NLP and they're working with these algorithms. So feel free to drop me an email, and maybe I can forward you the email to the experts.
Thank you, Matthias. So we've had another question that says, my understanding is that human reflexes and an instinctive response to danger cannot be bypassed. Are self-driving cars trained using machine learning or AI, etc., and how safe are they really?
That's a very big question, and a very good question as well. This is obviously ongoing work. So some researchers claim that by now self-driving cars are safer than humans. They probably make decisions. They make decisions in a different way. One thing you can think, the reaction time of machines is of course much faster. So if let's say you see an obstacle on the street, you want to perform an emergency braking, it takes around 300 milliseconds between you wanting to perform emergency braking and your foot actually starting moving, and then probably another 50 milliseconds or so before the car starts decelerating. So these 350 milliseconds, something the machine can do in 1 millisecond, probably. So let's say the machine can process the information at the same time as you can. It can act faster. The other thing is that machines don't have, a lot of accidents happen because people are not paying attention on the road. They're playing with their phone, or maybe if they've been driving the whole night, they're sleepy. So a lot of accidents are caused due to inattention, and that's something we solve with machines because they don't suffer from that fact. They can attend, and they can attend to many locations at the same time. They can look to the front and the back and the left and the right at the same time and process all that information. So in principle, they should be safer. This is a bit tangential maybe to your question. There's some questions on there's some dilemmas, let's say, on you know, what a machine should perform in particular cases. If you can't avoid, let's say, crashing into an obstacle because there's several obstacles, you know, what choice should you make? But this goes into ethics, and that's a big unsolved question. But I guess the bottom line is, if you will look at death statistics, let's say how many humans die in traffic every year, I'm convinced that, you know, in a few years or maybe in 10 years from now, the stats for self-driving cars will be much lower. So many less people will die in traffic with self-driving cars than today.
Great, thank you very much. Just one final question then. So do you think that artificial consciousness exists, or is it simply a deep neural network?
It's very interesting question, and very complicated question. And if you ask researchers working in AGI, it's artificial general intelligence research. That research is geared towards developing something that has general intelligence capabilities like us. So everything we talked about today is something some people call narrow AI, right? Something that can, you know, an algorithm that can classify sea trout and salmon. It can't play chess, but we can do all of these things. So we have this general intelligence capability. I've just watched a podcast by Ben Goertzel, who's he's been doing AGI research for, I think, 30 years or so, 20, 30 years. He says deep learning is not the answer to general intelligence. I think the big question is if consciousness is just a computation. So if all there is to our mind is the brain is, and all there is to the brain is well, it's not all of it, but a lot of it is just electrical activity and neurotransmitters. If this is all that gives rise to consciousness, there's no a priori reason that this couldn't be realized in a computer. And then by logic, you know, it follows that artificial consciousness should be possible. Probably we're still decades away from that, but unless we gain some new insights on the nature of consciousness, which is something we also don't fully understand, you know, what consciousness is in humans. Unless there's something that, some new insight that we gain, I don't see a reason why machines can't be conscious.
Okay, thank you very much. That was really fascinating, really interesting, and we had some great questions as well. So thanks everyone for participating. We're going to finish the session there, but as I say, if anyone's got any further questions, then feel free to get in touch either with the CPD unit or with Matthias. So thanks very much.
Thank you very much. Okay.
Bye-bye.
Bye.